Check it out now, y'all.
NanoHub U, online instruction.
Hello and welcome back to week 5 of NanoHub U's Introduction to Bioelectricity. In the preceding 4 weeks, we've begun with, in week 1, anatomy and structure of the nervous system through the derivation of the Nernst equation, describing how electrical potentials or resting potentials are generated in neurons. In week 2, we talked in a little bit more detail about ion channels, neurotransmitters, and how neurons communicate between one another. In week 3, we began diving into mathematical models that describe the electrical behavior of signals in cells. And we did that first with a core conductor equation and then with a cable equation, which worked for passive signals. In week 4, the last week, we talked about Hodgkin and Huxley. Initially, we talked about the two men behind the discovery that led to the Nobel Prize in 1963. And then we began talking about the equivalent circuit model itself, followed by the derivation of the equation. And then we spent the last 2 lectures of week 4 talking about predictions that were made from Hodgkin and Huxley and how those predictions have borne out, how they've turned out to be verifiable in an experimental setting, the ultimate test for the value of a model. In week 5, what I would like to do is begin to bring all of the ideas that we've discussed and all of the new concepts that we've introduced over the course of the last 4 weeks into the application of bioelectricity in clinical medicine. So there are a number of conditions, far more than I could possibly cover in a single week, but I have selected 5 from that large number to go into in more depth, and I will cover 1 in each of the following 5 lectures. Today, I want to talk about Parkinson's disease. And Parkinson's is a very nice extension of the work that we did in week 1 when we introduced simple neural circuits. So if you recall from that very first or second lecture, when we talked about neural circuits, we talked about neurons that are afferent. They go to the brain and they carry sensory information to the central nervous system, in this case the spinal cord. And then we talked about neurons that are efferent. They leave the central nervous system and go back to the muscles, and they carry motor output information. So there's sensory neurons and motor neurons, and then there's a third kind of neuron, these inner neurons. Whereas the sensory and motor neurons are excitatory, the inner neurons are inhibitory, and so you get a result that if you have a stimulus, because of a stretch, for example, in the extensor muscle here, you're going to have a excitatory signal coming back to the spinal cord and exciting the extensor motor neuron, and because of the inhibitory inner neuron, inhibiting the flexor motor neuron. So if you've forgotten this before going any further with this lecture, I encourage you to go back to lecture 1.2 and revisit this material, because what we're going to talk about today builds dramatically on what we learned here. The other thing we talked about is the anatomy of the brain and how the anatomy of the brain can be explored by taking cross sections of the brain, the hemispheres themselves. And we have 3 different kinds of cross sections we can do. We can do a sagittal cross section, which goes right down the middle of the head like so. We can do a horizontal section, which goes across the middle of the brain like so. Or we can do what's called a coronal section in this plane here. And that's what we're looking at here. We're looking at a coronal section of the brain showing the basal ganglia. And the basal ganglia are these structures in the brain, the caudate, the putamen, the globus pallidus, that are intimately involved in motor control. And it's the basal ganglia circuit, which includes the structure in the midbrain called the substantia nigra, which can be divided into the pars compacta and the pars reticulata, based on the anatomical appearance of that structure under a microscope slice, that are involved in Parkinson's disease. Specifically, it's neuronal death in the substantia nigra, which leads to the observable motor symptoms that we see in Parkinson's disease. So if we look at the circuitry, what you have is you have descending excitatory inputs from the cortex. You have ascending excitatory dopaminergic inputs from the substantia nigra. And then you have a number of different interconnections within the basal ganglia that lead to a net excitatory output to the cortex. And the death of neurons in the substantia nigra changes that circuit. So before we talk about that circuit, also recall that we talked about neuronal diversity. We talked about all those different kinds of neurons that you can expect to see in the cortex. And so what we have here is a cross-section of the globus pallidus and the putamen with a caudate nucleus up above, showing the medium spiny neuron projections throughout the substantia nigra and between the various nuclei. And so you can see that you have a combination of dopaminergic neurons, which are the projections out of the substantia nigra. And remember, we talked about dopamine as an excitatory neurotransmitter in week 2. You've got these local circuit neurons, medium spiny neurons, and you have the cortical pyramidal neurons, which we're accustomed to seeing in the cortex, or that pyramidal shape that we've been drawing throughout the course when referring to dendrites and axon hillocks and all that sort of thing. So there's a great diversity of neurons at play in this circuitry, and it's much more complicated than what I'm going to talk about in this lecture. But I do want to say that you can string these neurons together and begin to understand how more complex circuits than the reflex circuits that we talked about initially are put together. So in this particular case, let's say that you have a neuron in the striatum. And that neuron from the striatum receives excitatory inputs from the cortex and projects. So the striatum, the substantia nigra, projects to the globus pallidus. It's an excitatory neuron. It has an inhibitory projection to one part of the globus pallidus and an excitatory projection to a different part of the globus pallidus. More on that in a minute. But it inhibits, in this case, the globus pallidus neuron, which projects to the neuron that's in the VA-VL nucleus of the thalamus, and that inhibits it. It also receives inputs from the cortex, but projects an excitatory signal to the cortex, which then projects to lower motor neurons. So here's a circuit. Now, when A is at rest, because it's inhibitory, if A is at rest, then it'll fire. When A is at rest, it won't fire. Because it's not firing, it's inhibitory, B will fire more. Because B is inhibitory, if it fires more, C will fire less. And because it's excitatory, there'll be a net decrease in descending motor excitation. So it'll be harder to initiate movements. Conversely, if A is firing more, then because it's inhibitory, B will fire less while A is firing. When it's firing less, C will fire more because it's not being inhibited any longer, and that'll lead to a net excitatory output of the motor cortex. So this is a simplified view of how you can stack these neurons together and how firing rates of different neurons would give you a different effect at the very end. So with that in mind, let's dive right into the two pathways that are involved in Parkinson's disease. The first and easier to understand is the direct pathway. And in the direct pathway, we're looking at neurons from the substantia nigra pars compacta that project in an excitatory fashion to the caudate and putamen. In the indirect pathway, we'll look at inhibitory projections. But here we're looking at excitatory projections to the caudate and putamen, which itself is receiving excitatory inputs from the cerebral cortex. The output of the caudate and putamen is inhibitory. It inhibits the globus pallidus internal segment, and the output of the globus pallidus internal segment is inhibitory on the VA-VL complex of the thalamus, which projects to the frontal motor cortex, modulating descending motor control with excitatory neurons. The indirect pathway involves projections from the substantia nigra that are inhibitory to the caudate and putamen, which leads to inhibition of the globus pallidus external segment rather than the internal segment, which projects to the subthalamic nucleus, which in turn modulates the globus pallidus internal segment, which inhibits the VA-VL of the thalamus, and on to the frontal cortex. Now, what happens to this circuit under Parkinson's disease? Under Parkinson's disease, here we have two brain slices across the medulla looking at the substantia nigra. And when we stain the substantia nigra, you can see that in a normal brain, you have a significantly darkened stain area. In a Parkinsonian brain, you have a much lower darkness level. So the neurons that are being stained, there are far fewer of them in the Parkinsonian brain. So there are fewer neurons in the substantia nigra, which is why one potential treatment for Parkinson's disease is injection with dopaminergic neurons or stem cells that will become dopaminergic neurons into the substantia nigra. But outside of that, you have a lower population of those neurons, and that affects the cortical circuit in two important ways. By decreasing the amount of dopaminergic projections out of the substantia nigra, you decrease both the excitatory inputs to the caudate putamen direct pathway and the inhibitory inputs to the caudate putamen indirect pathway. So let's go through these one by one and see what the net effect is on the frontal cortex. So if you have descending cortical stimulation on the caudate putamen, that remains the same. The substantia nigra is damaged, so looking first at the direct pathway, you're going to have less excitation of this part of the caudate and putamen, which means the caudate putamen, because it's excited less, will fire less, but it is inhibitory. If it fires less, it's going to inhibit less, which means that the globus pallidus internal segment will be more active because it's being inhibited less. If it's more active, it fires more, and it is inhibitory on the VA-VL, so when it fires more, you get more inhibition of the VA-VL complex in the thalamus, and more inhibition means that the VA-VL will fire less, which in turn means that you'll have less activity of the frontal cortex. So the net effect of neuronal cell death in the substantia nigra is less excitation of the motor cortex and less motor activity. A greater difficulty in initiating motor movements, for example. So that's the direct pathway. If we look at the indirect pathway, neuronal cell death in the substantia nigra will lead to less inhibition of this pathway of the caudate putamen. Less inhibition means that this part of the caudate putamen will fire more because it's not being inhibited as much. It fires more, but it's inhibitory, so this arrow gets bigger. It's firing more. More inhibition means that the globus pallidus external segment will be inhibited more and therefore fire less. So the projection of the globus pallidus external segment to the subthalamic nucleus will have less inhibition. If you have less inhibition of the subthalamic nucleus, it will fire more. It is excitatory, so when it fires more, it's going to excite the globus pallidus internal segment more, making it fire more. And when the globus pallidus internal segment fires more, it inhibits more, so you have more inhibition of the VA-VL complex of the thalamus, making it fire less, which leads to less excitation of the frontal cortex, and it's the same end result as we had from the direct pathway. So whether you're going from the direct pathway or the indirect pathway, really they sum up at the globus pallidus internal segment, with the direct pathway leading to less inhibition during Parkinson's, and the indirect pathway leading to more excitation during Parkinson's. Either way, you get more activity of the GPI, which leads to greater inhibition of the thalamus and less excitation of the frontal cortex. So this is the circuit going both ways and how it is affected with Parkinson's disease. It's very, very important that you be able to look at the circuit and walk your way through it, as I've done here, in the same manner that you were able to back in week 1, walk yourself through the knee-jerk reflex, or the muscle stretch reflex that we talked about, or the vestibular ocular reflex that we talked about in week 1 as well. So all of those reflexes are important. This circuit is much more sophisticated and much more exciting, really, from a medical standpoint. It's very important that you understand it. Now, as a neural engineer or a biomedical engineer, looking at this problem in the anatomy and trying to devise a solution, what you can begin to think of is you have all of these distinct anatomical structures that have been affected by damage in the medulla, in the substantia nigra. Because of the damage in the substantia nigra, we have this net effect that we observe symptomatically in Parkinson's disease. So how could you come in and overcome this disease? One way is through a pharmacological agent, like we discussed in week 2, using L-DOPA, which is a dopamine reuptake inhibitor, means that even though there are fewer neurons projecting from the substantia nigra to the caudate putamen, and those neurons are dopaminergic, so there's going to be fewer neurons, means less dopamine, you could take L-DOPA, which is a reuptake inhibitor, so what little dopamine gets released in the caudate putamen will act longer. That'll overcome the rest of the circuit. That's one approach. Another approach would be to come in with an engineered device and try to modulate the behavior of this circuit. And that's the approach that we're more interested in, for example, in my own laboratory. And so with an engineered device, you can think about taking a deep brain stimulator. So a deep brain stimulator, let me go back to the circuit, where we would take electrodes and we would position them in the subthalamic nucleus, and then we would try to compensate for the increased excitation out of the subthalamic nucleus by stimulating the subthalamic nucleus in a way that is inhibitory. So if we can come up with an electrical waveform that, when applied to the subthalamic nucleus, has a net inhibitory effect, then we'll decrease this inhibition and we will at least partially compensate for the increased inhibition to the VAVL and the decreased net excitation of the frontal cortex. And that's exactly what Medtronic's deep brain stimulator for Parkinson's disease does. So you have a pair of generators that are very similar to a cardiac pacemaker, and those generators are coupled to electrode leads. The electrodes are implanted deep into the brain, into the subthalamic nucleus, and they stimulate the subthalamic nucleus in such a way that you decrease the amount of inhibition coming out of the VA, or going into the VAVL, and you increase the amount of excitation in the motor cortex. And so you can see pre-stimulation, you can see the amount of recorded activity in the motor cortex. During stimulation, you can see that activity goes up dramatically, and post-stimulation, you can see that that activity goes back down. But there's nothing quite as effective as a demo, and so I've spoken with a gentleman in Australia who is a Parkinson's patient, and he has given me permission to show the following video of himself with a deep brain stimulator implanted, both when it's on and when it's off.
Hi, I'm AJ. I'm 39 years old and I suffer from Parkinson's disease. I was diagnosed 4 years ago when I was 35, and I've since undergone deep brain stimulation surgery. This is a procedure whereby 2 probes are dropped deep into my brain and hooked up via a wire down my neck to a pacemaker in my chest. This provides a steady stream of electricity to my brain per second. So it has had a major effect on my life and a major effect on my family's life, which is the main thing. And today I'd like to show you what happens when I turn my neurostimulator off. Now, it's just after 11 AM, so it's time that I had my second dose of medication for the morning. So my first dose is pretty much all but worn off. So this is a good example of what I'd be like when I'd be sort of off, with no medication in my system and no power. To show you the dramatic effect, I will demonstrate. This is me with the power on.
You're looking for the steadiness in his hands and his motor control, fine motor control.
I'm not making
and remember what this looks like now
faces
versus later.
Video. These are tests that the neurologists make us do to test our reflexes. As you can see, they're wiggling, moving fine, and I've got very good movement. This is the remote control, and this checks that I'm on. So on and okay. And this is me when I turn it off. You won't be able to read that, it's shaking too much. So it's almost an instantaneous reaction. I can't control this. Could shake some quality cocktails with the right. The left just looks like the royal wave. My voice is gone. It's harder for me to get words out and speak. I'm completely rigid, and if I tried to stand up, I'd fall. If anyone thinks I'm faking this, I'm not. I can't control the tremors and dyskinesia. The twisting in my neck is called dystonia and is really quite uncomfortable. So, as you can see, the tremors are getting much worse, and I'm in quite a bit of discomfort, and I'm about to drop the remote control, which will be fun because I won't be able to turn myself back on. So I think party time is over. Almost automatically. The power comes back on. I'm steady.
Extraordinary.
So, if anyone's considering DBS, I thoroughly recommend it. It is life-changing. Thanks.
It's hard to find a more dramatic example of the effects of neurostimulation delivered appropriately to interfere with the cortical circuit. So the understanding these circuits that you've been studying and learning about over the last 4 weeks has very real and very life-changing applications. And this, in Parkinson's disease, is just one of them. When we come back for the next lecture, we'll begin to talk about epilepsy. I'll see you then.